Hey everyone, I think we're going to go ahead and get started. Let me just share my screen real fast. Everyone can see that. And good morning, and welcome to WCEC's Affiliate and Partner Webinar Service. Today's webinar topic is Multifamily Air Tightness Standards and Testing. California Building Code requires infiltration testing for new homes, but no standard exists for multifamily buildings. Part of the reason is that they are difficult to test. A common method is to test the whole building at once, but this is expensive and quite complicated. An alternative called a compartmentalization test is conducted on individual units at a time. Compartmentalization testing advantages have these testing advantages. Units are safer in a fire, healthier because they inhibit the passage of smoke and smells between neighbors, and they make ventilation systems work better. The problem is it's hard to get apartments tight. So in this webinar, we will review Stephen Winters Associates' database of over 600 blower door tests and what we've learned from it. We'll also review some recent work by WCEC, which is developing an automated sealing process to compartmentalize units. Our speaker today is Sean Maxwell, Senior Energy Consultant for Stephen Winters Associates. I am Paul Fortunato, the Outreach Coordinator for WCEC and your host of today's webinar. Webinars are a service provided by WCEC to help inform and guide potential energy efficiency decisions for utility DSM programs and beyond. We at WCEC hope you find these webinars valuable, as they are only offered live to our affiliates and partners who support this research. To help ensure the information in these webinars remains relevant to you, our valued partner, I welcome any and all feedback, including topic recommendations. So please do not hesitate to call or email me with your ideas to enhance the value of these webinars. I will be providing a contact slide at the end of this webinar, so you may quickly get in touch with me or the featured speaker. If you have a question regarding today's presentation, you may ask it directly in the chat panel, or if you would like to speak to the presenter and the audience, you can request to be unmuted from the chat panel. I will be monitoring the questions panel and will save the questions and ask them to our presenter in the order they appeared at the end of the presentation, or as per the request of our speaker, you may ask your questions at any time. The webinar will be recorded, so if you'd like a copy, please contact me. I'll post our contact information again at the end of this webinar. Today's topic, once again, is Multifamily Air Tightness Standards and Testing. Now let me welcome Sean Maxwell. Sean, let me go ahead and get this. Are you there, Sean?
Yes, I am.
Great.
So share my desktop. Okay. Are we live?
Yes, we are.
All right. Great. Okay. So thanks, Paul. Thanks for having me here. My name is Sean Maxwell, and I'm from Stephen Winters Associates. I think there's probably we've got a pretty small crowd here today, so please stop me at any time to ask questions. I really want to engage with people. So, Paul, if people are typing in questions, feel free to stop me at any time, and so that we can make it a bit more interactive so people can get something out of this. So I could talk about multifamily air tightness standards and testing forever because it's something I'm really passionate about and something that I think is pretty important, and I think we're starting to see a lot of other these programs and codes recognize its importance as well. So I've been at Stephen Winters Associates for almost 7 years, and before that I was at Conservation Services Group, where I did a lot of blower door testing at CSG and here at SWA. So mostly in New York, I've been working on larger multifamily buildings because that's what they build here. They're all masonry because you're not allowed to use wood. And we've been doing mainly compartmentalization testing, which is single unit testing. So I'm going to talk about the different kinds of testing and the benefits and advantages of each. Okay, so this might seem obvious why we do testing. we test air leakage with a blower door because it verifies that the air barrier is correctly installed. And that's important because infiltration is a huge driver of heating and cooling loads, or it can be. So for multifamily buildings, though it's not as simple as a single-family home test, the standards, there actually aren't that many really well-developed standards that are widely used, and so we've got a lot of different ways to test a multifamily building. So let's go over a couple of them. The simplest kind of test you can do is just like you would on a single-family home with a single blower door in the front door, and you depressurize the entire envelope at once. Pretty simple, and you basically isolate only exterior leakage by doing that. So the only measurement, the only airflow you're measuring is that coming through the exterior of the envelope. So similarly, when you do a whole building test version of this, you'll usually need multiple blower doors, and you'll need to open up doors to interior spaces to facilitate airflow between the zones. And you're going to need multiple fans and multiple operators, and pretty much you need an experienced, coordinated team. People who've done this before, people who understand how the equipment works and how to coordinate a whole team of people to depressurize an entire building at once. This testing, I love doing this kind of testing. It's there's just so much going on, and there's lots of smart people running around. I've gotten to do whole building tests with some real leaders like Terry Brennan before, and that's pretty cool to do a whole building test with someone like that. Another way you can do multifamily testing is with guarded blower door testing. And I hope I'm not going to bore you with details if you already know what this is, but guarded blower door testing is trying to isolate the exterior leakage from the envelope by using multiple blower doors to balance pressures across parts of the building that you don't want to measure leakage from. So it's a little bit difficult to understand, so I'll go through some graphics. With this type of testing, you also need multiple pieces of equipment and multiple operators, and you need an experienced team. So this kind of testing is pretty common for buildings like townhouses where you have multiple entries and there's really no good way to do the whole building at once. So you have to use multiple doors and then turn them all on at the same time and coordinate them so that you get the same pressure across all of the townhouses at a time. Let me know if you have any questions up until now. So this is me. I'm doing a simple guarded blower door test on two of the offices in our office, just for illustration. So I've got two offices side by side, and I'm going to do a guarded blower door test so I can know what's the exterior envelope leakage of that office on the right. So a simple test is you put a blower door in apartment B, that's your target apartment, and you bring it up to 50 pascals of pressure difference. So the red line around it shows 50 pascals around all four sides. And then on the left side, you have the fan is off, and you've got much less than 50 pascals. So the next thing you do is you turn on the blower door in apartment A up to 50 pascals, and now the pressure difference across these two apartments is equal. So you've got 50 pascals all around and 0 pascals across the shared boundary. So in the last test, 528 CFM was the total leakage from that apartment. And this test, you have a measured leakage from apartment B of 347 CFM, so it's less. So the difference between those two numbers is the inter-unit leakage. That's 181 CFM. And we sort of disregard that number. The total for both apartments, doing an unguarded test, or just a total leakage test, is 1,085 CFM. but the total for both offices with a guarded test, meaning they're both at the same pressure at the same time, 744 CFM. So it's much lower, and you can see 300-something CFM is coming from that shared boundary. And from there you can get much more complicated. So this is a blower door test. Apartment B is in the middle, and then we've got apartments A and C on the left and right, and a corridor below them. And you depressurize all of these zones at the same time and equalize the pressure across each. And then you can isolate the leakage from apartment B, so you know that the only airflow you're getting is from the exterior envelope of apartment B. So that's a way to get that number, which then you can use in an energy model. So the last kind of testing you can do for multifamily, or another kind, is single unit testing, where you use just one fan and one guy or gal, and you test a single apartment at a time. So you just move it around the building. This is also called a compartmentalization test. So the drawbacks of that kind of test are that it doesn't isolate the exterior leakage, so you can't get this number, which is pretty important for an energy model. So energy models don't account for inter-unit leakage, and if you've got airflow from one heated zone to another heated zone, who cares, because there's no energy transfer there. So compartmentalization testing gives you this number that is not really good for an energy model. So it's hard to base utility incentives off of compartmentalization tests. So for a HERS rating for a single-family home, you can get your HERS score down by reducing your air tightness, or you can increase your air tightness, and in some cases get more incentive money for a better HERS score. So, but you can't do that with compartmentalization testing because you don't get a number that you can use for energy models. The drawbacks of whole building testing and guarded blower door testing are that it's expensive, and you need this big team who's done this before, and it's also hard to do this complicated setup early in the construction process because you need so many people and so much equipment. It's not easy to set this up, during an earlier point of construction when you might be able to use the information to guide progress. The other reason that it's not as good is that it does fail to catch these inter-unit leaks, which I'm going to go in depth into why it's important that we catch them. So the benefits of compartmentalization testing, these single unit tests, are that, well, recently we've been talking to the New York State Code folks to try to get them to include compartmentalization testing for multifamily. They're considering adopting IECC 2015, and that has blower door testing in the language, but there's really no good way to implement blower door testing on a statewide level using whole building tests. It's much easier we think, to mandate compartmentalization testing. It's just a lot easier to describe, to define, to have standards for technicians. We already have a network of trained professionals, HERS raters and BPI professionals, who know how to do this test. And I think in the end it's cheaper than other methods of testing. And I'll go into that a little bit. I also think it's very useful to builders during construction because you can set up a blower door pretty early in construction as long as you have power, and find some pretty big leaks between apartments and also from the exterior. So I think it's low cost, to set up. If you have a builder who's building 50 apartments or 50 houses, you can just the builder can buy a blower door himself and use it to test along the way. So I think it's useful during construction as well. So let's talk about the costs a little bit. So Don Hynek, who I respect very much, wrote an article for Home Energy magazine where he describes a 50-unit test that his team did. They used 6 technicians, and he estimates the cost for the whole shebang was about $6,000, or about $120 per unit. And right after this, if you want to, there's actually a webinar put on by Retrotech, the blower door manufacturer, and they're going to go over multi-fan testing for large buildings. This kind of testing is, like I said, is pretty fun to do and fun to watch. Lots of blower doors and computers everywhere. But I think it's pretty expensive in comparison to compartmentalization testing. So there's a lot of numbers to look at, but looking at 2 different building types, one with a shared single entry that's like a interior hallway, multifamily building, and then a townhouse configuration, we can look at the difference in costs. So, for example, a 10-unit building might take 8 man-hours to prepare the units and then run the blower door test, and just based on some pretty basic assumptions of airflow, you probably need at least 2 blower doors for that to meet code levels of air tightness. So we think the cost of that might be $1,120. By contrast, same number of units doing compartmentalization test, it probably is less than that because you can, especially at larger buildings, you can do sampling to demonstrate compliance. So for larger buildings, say this 100-unit building, it might take 16 man-hours because you would need to do a number of tests, but the total cost for the whole thing, if you have basically 2 people doing this test, two people one full day at $90 an hour plus a mobilization fee, you're looking at about $1,600 compared to about $8,400 doing a whole building test. And just as a check, Don Hynek's example of 50-unit building costing about $6,000 using this method of estimated costs, it would be around $4,500. So it's in the ballpark. For townhomes, it's pretty similar situation where doing compartmentalization tests one after the other is easier than doing whole building or guarded blower door testing because there's not the multiple pieces of equipment and multiple people required to do that many tests at the same time. So does anyone have any questions so far? Paul, how are we doing?
We're doing great.
All right.
But we don't have any questions just yet.
Okay, great. So benefits of compartmentalization, I think anyone on this call probably would agree. There's lots of benefits to it, so I'll go over some of them briefly. Safety is a big benefit of compartmentalization. So one of the main tenets of fire control and smoke control is passive fire protection by use of fire barrier materials like drywall and caulking and fire stopping. But one thing that I've found over the years inspecting buildings is that there quite often is there's an inspection of the fire-stopping materials, but not really an inspection of the fire barrier as well as there should be. So on the left, we have pictures of highly visible red fire stopping. It's red all over, so you think the air barrier is there. And we have these putty packs on these outlets to prevent smoke transfer between units. But in this same building, there is missing drywall behind the tub. I mean, this is several square feet of missing drywall. So this building passed its special inspection for fire stopping, but obviously there's some problems. This leak on the right, the drywall behind the tub, is harder to find. You have to crawl around to look for it. Whereas the pictures on the left, you can see the nice bright red fire stopping, and so there's your verification. If we do blower door tests on individual units, we would find leaks like this, missing drywall behind the tub. So is this an energy issue, or is it a life safety issue? I don't know. I guess it's whatever your priority is. But I think certainly doing blower door testing can help us really verify that buildings are actually being compartmentalized. Better ventilation performance is another benefit from compartmentalization. This is actually where I got started in this, where we were trying to determine where the airflow is coming from in apartments, exhaust-only apartments where there's an exhaust fan and no dedicated fresh air. So we want to find out if there's exhaust coming out of the building, where's the air to replace that exhaust coming from? Is it coming from the corridor door? Is it coming from other apartments or from the exterior envelope? We tried to quantify that, and we basically came to the conclusion that air is going to come from all over the place unless you hyper-compartmentalize the unit. We have some examples of apartments that were hyper-compartmentalized and that these passive ventilation systems finally work. So it can improve ventilation performance. Just looking at two buildings with different levels of air tightness. The one on the right has about 53 CFM average exhaust coming from an apartment, and the supply from passive vents, in this case it was an airlet through wall vent, was an average of 4.3 CFM, which is not that much. By contrast, we have another building where the average air change rate was 2.5 ACH50, and the exhaust was 41 CFM. We've got 11.5 CFM coming from trickle vents in the windows. So tighter apartments deliver more air from the places it's supposed to come from. So the air from the trickle vents is coming straight from outside. That's fresh air. The buildings that are not compartmentalized, the air more often comes from leaks from other apartments through penetrations, plumbing penetrations, electrical penetrations, and through the corridor door. So obviously those are not places that we would consider fresh air. So does compartmentalization lead to energy savings? Every time I ask someone like Gary Nelson at the Energy Conservatory, he would say, probably, but I don't know how much, and I can't tell you. It's too difficult to figure out. But the theory is that if you compartmentalize a unit, if someone does something like open a window because it's too hot in their apartment, in a non-compartmentalized building, you'll get lots of airflow into that apartment through shared walls and floors, whereas in a compartmentalized building, that airflow will be stopped by the substantial air barrier on this compartmentalized unit. In order for that to actually be the case, the apartment has to be pretty well sealed. So if your exterior envelope is sealed to 3 ACH50, your apartment envelope has to be sealed at least to 3 ACH50 or less in order for that effect to actually, for that to work. So making apartments airtight is not actually rocket science. It's pretty straightforward. It's just difficult to do. Buildings are made out of literally millions and millions of separate parts, and so putting them all together so that they make an airtight piece is pretty challenging. But there's ways to go about it. This philosophy is using an airtight box for the exterior of the envelope of an apartment, and then any interior partitions get applied on top of that airtight box. So this is just basic fire stopping. So using drywall and layers accomplishes this. So this is on the left, this is right near a kitchen in an apartment where you have, this is a countertop on the left, and these pieces have been applied to the drywall completely inside of the air barrier. So one goes on top of the other, and they are all airtight boxes. This is just construction sequencing. On the left, we have a good example of drywall going all the way from floor to ceiling and being sealed to the top, the bottom of the floor above. So that's great. And then there's a drop ceiling in this closet, but that's applied after this air seal has been made. So that's good technique. On the right, same building, different apartment. Drywall goes all the way from floor to ceiling and attaches to the underside of the floor above, but there are a lot of big holes for electrical penetrations. So obviously this is something that needs to be fixed. So we also think this, I guess you could say there's a way to get apartments more airtight, and that's to cheat with some cool gadget. So I got to work with UC Davis and WCEC with Curtis Harrington and Mark Modera there, who are using an aerosol process to seal apartments, and this stuff really works, and it was really cool to be involved in. So the basic setup is on the left picture you have an air compressor and then a pump that's pumping sealant. It's a non-toxic building sealant, like an adhesive, and that pumps this liquid to these air nozzles where air rushes out of the nozzles and atomizes these sealant particles, so they float around in the air for a while. And then you put a blower door in the apartment door and pressurize the apartment. So this positive pressure is pushing air out the leaks, and as it's doing so, it's carrying these sealant particles on the air currents and depositing them in these holes. So, and the stuff actually works. And so I'll show you some results. Setting up this process is pretty straightforward. We went around and got very big holes with a spray foam can. Took maybe 15 minutes to do that because it's just faster to do that than to wait for the sealant to do it. We also swept away debris from some easy-to-seal leaks here along the bottom here so that the aerosol could get at it, the bottom of the wall. And the results are pretty dramatic. So before sealing, each apartment was over 500 CFM 50. And after sealing, each one was over below 200 CFM 50. So that was an average reduction of 70%, which is pretty amazing. So you can see in this apartment the leakage went from 660 CFM down to 190 CFM. We tested the air leakage a few times during construction and noticed that in some cases the air leakage can actually go up because this seal created by the aerosol can actually be damaged by workers doing things like disturbing some of the seals on electrical outlets as they're working, or making new holes, things like that. So in one case, the leakage went up. But still, in that one apartment, the leakage was below 160 CFM, so that's still very good. This is a graph of what the leakage in the apartment looks like as the apartment's being sealed. So we did 4 apartments where we monitored the pressure during sealing, and you can see that it's pretty steady up near maximum leakage for a minute or two as the sealant goes into the apartment and it starts floating around, and then it starts collecting on these leaks. And as it does, as it collects on the leaks, it starts reducing the amount of airflow required to keep that apartment at 100 pascals. And so it gets lower and lower and lower until it starts evening out at some point. So pretty neat process. So this is what the sealant looks like. This is an outlet before, and this is another outlet after. This sealant feels a little bit like putty. It's a little, not exactly sticky, but it's tacky. So these outlets had been covered with masking tape before because the apartments were about to be painted. So that actually kept the outlets nice and clean. And you can see that this gaps as big as this can be pretty easily sealed by this aerosol. Some other ones that are pretty hard to do by conventional means are, on the right, this is an electrical penetration where it's pretty hard to seal that with caulk and do a good job, but the aerosol does that automatically. Also, this gap here is along the bottom of the drywall, along the floor, and that gap is extremely hard to seal because it's on the underside and it's difficult to get a caulk gun under there, but the aerosol sneaks in there and seals that up very easily. So after this was done, we went through and measured, well, before and after, we measured leakage from discrete points with a modified duct blaster and a low-flow plate to measure leakage before and after sealing. And we found some pretty good results. So this is a graphic of all the leakage measurements we took in one apartment. So you can see there's a lot of these red numbers here are leakage points through all these outlets here. There's a light penetration here, switches, mostly electrical penetrations. And along all these walls, these leaked significantly. One thing of note for this building was this was an ICF building, an insulated concrete forms building. So the exterior wall was actually poured concrete, so it's a pretty darn good air barrier. As a result, the interior walls applied to that airtight exterior wall were completely sealed even before the aerosol. So that was interesting to verify. this is before the aerosol, and then after the aerosol, oops, yeah, I forgot that they also use this is that picture from before, the layered drywall approach. And the walls that they used that approach on, the leakage from those walls was 0 to begin with. So again, effective drywall layering will do a lot for effective air sealing. After the aerosol, basically any leak that we could measure, we did measure, and couldn't measure any leakage. The instrument only goes down to about 2 CFM, so we couldn't. There is probably some leakage coming from some of these, but if any, it's less than 2 CFM. That's pretty darn airtight. So it basically went from this much leakage to basically 0 pretty much everywhere. And the type of leaks that this sealed we could only measure these point source leaks. So in one of the apartments, 27% of the leakage that was sealed was from those electrical penetrations and things and plumbing penetrations that we could put that device over. There were some that we couldn't. There were some leaks that weren't sealed at all, and that's, say, 28% in apartment 202. But then there's a whole bunch of leaks, almost half, that we couldn't measure because our device can't, say, fit over the crack along the bottom of the drywall. But a large majority of leaks were sort of unidentifiable leaks that would be difficult to address if you told a contractor, here's a caulk gun, go around and seal as many leaks as you can find. He's probably not going to be able to do much better than this 27% leakage reduction here, because these other leaks are a lot smaller and more numerous and more diffuse. So this aerosol process does a great job of finding and sealing small, difficult to find leaks. So just some results in other ways of looking at things. We tested 9 apartments in the same building, all near each other. So these top 3 are on the 4th floor, these 3 on the 3rd floor, and these 3 are on the 2nd floor. The ones in green are the ones that had aerosol, and the ones in red and yellow didn't have aerosol. You can see, though, that the aerosol actually had an effect of lowering the leakage of some of its neighbors, which is pretty cool to find out, that you could seal one apartment and it will also affect the other apartments near it. So that's pretty cool. So as a result, actually that's the same slide. Operating pressures in these apartments were a lot more significant. So the reason we care about this is we measured the pressures in these apartments because we wanted to know what is the pressure that this apartment is running at normally, and because that is what draws air through these vents, the fresh air vents. So if you don't have enough pressure, you're not going to get air coming from the vents like you want to. This is actually supposed to be 11.5 here, negative 11.5. The apartments where it had been aerosol sealed, significantly higher pressure than some of these the other non-sealed apartments. So it really does help make the ventilation system work better. Here's just a side-by-side comparison of 2 apartments. We measure the pressures while manipulating various things like opening the window, closing the vents, turning the bath fans on and off. And you can see, just to simplify this slide here, on the top floor, or sorry, the top graph, you can see changing these things didn't really have much effect on the pressure in the apartment, manipulating the pressure like we'd like to. This is an apartment sealed to 0.27 CFM50 per square foot, which is not that tight. In the apartment that had been super sealed, we could basically do whatever we wanted to it. You could make the pressure go up, you could make it go down by opening and closing these vents. And so we're very confident that we're actually going to be getting air from these fresh air vents like we want to. So if we want to recommend compartmentalization on, say, a statewide level, what is realistic? This is a chart showing results of 600 of these compartmentalization tests that we've done. So the Energy Star multifamily high-rise and LEED for homes standard is 0.3 CFM50 per square foot. 12% of the apartments were that leaky or above, but 88% of them were tighter than that standard. And that's the standard that we recommended for New York State for their energy code. So is that too tight? Well, every apartment that we tested was going through some green construction program, like New York's NYSERDA multifamily performance program, or LEED, or Energy Star, something like that. So all of them were doing some sort of green construction program. So maybe it's not representative of the building industry at large, but it does make you more confident if 88% of those apartments can meet that leakage standard. This is sort of another point that we want to make, that in order to use those passive vent strategies, which are allowed by some codes, you need super, super tight apartments like those ones that we saw with the aerosol in order to make those super tight apartments draw air from the passive vents. So that's sort of another story, whether those passive vents should be a way to provide fresh air. And as I mentioned, we recommended 0.3 CFM50 per square foot as the code level for New York State. I'm not going to go into this too much, but this is just for your reference. This is what we recommended to New York State for their blower door code. To summarize this page, it says basically you need to do blower door tests on each individual unit at 50 pascals using ASTM E779. For 1- and 2-family homes, we recommended that they go with a metric of 5 air changes per hour in climate zones 4 through 6, which is New York State, which we think is a pretty achievable standard for this day and age. And for multifamily buildings, we think 0.3 CFM50 per square foot is the way to go. So that specifically calls out compartmentalization testing, and we think that's important and is going to move the building industry forward in some important ways. We also included, this is a very thick paragraph here about sampling. So we also think that sampling should be allowed in New York State to comply with compartmentalization testing. So that's really all I have on this topic. So, Paul, if we have any questions, that would be great. If not,
yeah. Well, thank you, Sean. Right now, we don't have any questions. And I actually have Curtis here as well. He's just see how you were going to present this.
Great. Hello, Curtis.
Hey, Sean, how's it going? No, not particularly. I like the data that you presented. I haven't seen some of that newer data comparing the tight envelope with the leaky envelope. in terms of the pressures within the building itself. That was interesting. Yeah, I just happened to hop by work today because I'm on paternity leave, but so I appreciate you presenting.
Sure. Well, I think we're putting together the report on that pressure testing we did in the building that we aerosol sealed, and that should be done really soon. So I'll send you all the data from that.
Okay, Sean, there is one question. If you go back one slide, how many air changes per hour did you suggest for climate zone 3 through 6?
Well, we didn't suggest, because it doesn't exist in New York State. So, I mean,
okay.
For other, I think in the IECC, which is what New York State was planning to adopt, it's 5 ACH 50 for climate zones 3 and lower, which is anything further south, basically, than New York City, or anything warmer than that. But we think that 3 air changes per hour is too hard for New York State to achieve right off the bat.
Right.
So we recommended 5 air changes per hour. So I saw a comment, not sure if I can get that back. Someone said it's actually, I think it's
air changes per hour in climate zone 1 and 2.
Okay. Yeah, so for New York State, it would be 3 air changes per hour, but we recommend that they go no lower than 5 to start with.
3 air changes per hour is actually a pretty hard out, either of planning on the part of the contractors or adding something like the aerosols to it.
Right. Yeah, I mean,
the ASHRAE 62.2, isn't that around 3?
No. ASHRAE 62.2, it was 0.2 CFM50 per square foot, and they changed it to 0.3 CFM50 per square foot. So that's around 0.3 CFM50 per square foot is around 6 to 6.5 air changes per hour for an apartment. So that's, and of course it depends on the apartment geometry, but around there.
Okay. I didn't realize they changed the metric.
Yeah, the standard was, it's written in the standard as 0.2 CFM50 per square foot, but I got it from Terry Brennan himself that they plan to, or they approved this addendum, but it hasn't been published yet, to bring it to 0.3 CFM50 per square foot.
So are any more questions from the couple here in our audience?
Thank you.
Okay, well, if there's no more questions, or if you have any questions afterwards, that's normally what happens to me in these situations, is I come up with something the minute everything gets turned off. You may contact me directly, and I can send it off to Sean.
All right.
With that, I would like to thank our speaker. Thank you so much for joining us, Sean. And thank you to those who have showed up. I know it's basically everyone's holiday at this point, so thank you for joining us.
All right. Thank you. Thank you, Paul. And thank you, Curtis.
Thanks, Sean.
No problem, Sean.
Have a good one. And you know, enjoy your time in Australia.
Thank you very much.
All right, take care.
Bye-bye.